Hi, in today's video we will quickly find inductance of a toroid. Have a look at the figure on your screen. A toroid is basically nothing but a solenoid bended or reshaped in form of a ring. So, if you can have a core material with some permeability in shape of a ring, and if you wound current carrying conductor over this, you will get a toroid. So, the best way to visualize toroid is the solenoid which we have seen in the previous video. You just take that solenoid, and if you can bend that into form of a ring, then it gives me toroid. Okay. So I hope now you have some physical structure in your mind regarding toroid, or you can Google it and find it out how exactly a toroid. So many toroidal experiments available in YouTube videos, so even that you can watch as a supplementary to understand this video better. Okay, now my intention is to just make you understand how to derive a mathematical expression for finding inductance of a toroid, such a physical structure. So as usual, the current flowing in toroid is assumed to be capital I, and the cross sectional area of the toroid is taken as capital A. So we know that from the discussion about the previous videos, the flux linkage, right, the total flux linkage lambda is nothing but the total turns multiplied by magnetic flux, and this magnetic flux can be written as B into A, flux density into area, and magnetic flux density is nothing but permeability of the medium into intensity, magnetic intensity. So I can write it as N mu H A. Now if I know what is H for a toroid, that is magnetic field intensity due to such a shape, then I can substitute the value here and find out what is the total flux linkage. So magnetic field intensity inside the toroid is given by equation H is equals Ni 2 pi r, Ni 2 pi r, okay, where r is the radius of toroidal ring. So how we measure r is given in the figure. Okay, we measure it with the inner radius, in the sense we take the axis of this toroid, and from the center we measure till the axis, that is the radius of the toroid. It's not either inner radius or the outer radius, please remember. Okay, so that is my r. So we usually say radius of toroid. Okay, we call it as radius of toroid, but it's better to know how it is measured. Okay, Ni by 2 pi r is my H. If I know this is my H, then I can better write flux linkage as N mu. Just substitute this H as Ni divided by 2 pi r into A. So this Ni by 2 pi r is nothing but H. And further, okay, N into N is N square. So I will write it in a better format. So I can write it as mu N square Ia divided by 2 pi r. So this is my total flux linkage. Now as you know, the inductance is defined as the ratio of total flux linkage by the current carried, right? So lambda by I. So this becomes mu N square Ia divided by 2 pi r, and I have I here, and now this I and this I cancels out. So finally I end up with my L, that is inductance, as mu n square A whole divided by 2 pi r. So this much of Henry is my inductance of toroid. Now as you can see here, 2 pi r gives me the entire perimeter of the toroid. A is the cross sectional area, n is number of turns, and mu is the permeability of the medium. So it directly tells you that the inductance is not going to depend on the amount of current flowing through the toroid. Okay, this is interesting. In the previous video also we have seen the solenoid equation doesn't have any relation directly with the current flowing. So it depends upon physical parameters. I can say that the inductance of solenoid or inductance of toroid basically depends upon the physical parameters of the toroid. Basically the inductance, okay, which is a physical quantity, directly depends upon the physical parameter. The fellow who is responsible for inductance is nowhere in the picture. That's interesting. Okay, so if you can fix the radius of the toroid, cross sectional area of the toroid, number of turns of the toroid, then accordingly you can vary the inductance of that toroid. You should not worry about how much current that toroid is going to carry to calculate the inductance. Yeah. So that summarizes this video. Thank you.